Okay, let's get started with class today. We're gonna start with the sample classification topic. So we mentioned in the previous lecture that after you get the expression index, we can look at all the samples across all the different genes. And besides looking at the differential genes between some conditions, in this case, say we are interested in, for example, samples that are related to a disease. And so you collect the normal tissues, you collect the disease tissues, you do RNA-seq analysis, look at the expression. We are interested in what genes are different between the normal and disease, but also sometimes you might have a new sample coming in and you want to do a diagnosis to decide whether this new individual is normal or is the diseased sample. And so that's kind of a classification question. Can we learn from the existing samples to see, what this new sample belongs to? And so classification is really the same as machine learning, at least a type of machine learning methods. The basic task is to assign an object to a class based on the measurements on this object. For example, is this sample normal or cancer based on the expression profile, right? So in this classification method, there's unsupervised learning, which is what we will cover today. In this case, initially, we will try to ignore the known class labels. So we don't try to learn the features between the disease and the normal or the two classes. We just try to somehow cluster them and then see where this new sample belongs to. So we just want to know which known sample is the unknown sample close to. And then try to predict what this unknown sample is. So today's lecture is going to be about unsupervised learning. But on next Tuesday, we will teach you about supervised learning, which is if we know the tumor normal in a cancer setting, can we extract some useful features based on the known class labels in order to best separate the classes? And then once we can separate those, we can use the new sample and then use the same features to predict whether that unknown sample is, which class does the unknown sample belong to. Okay, so that's for next lecture. So for the unsupervised learning, the very simple approach is to do sample clustering. So for example, this is one of the earliest studies where people are at that time looking at genome-wide gene expression. At that time, it was microarrays, and now you can do this with RNA sequencing. If you were to take enough samples from, this is patients with breast cancer, and if you just take those breast tumors and do profiling, and after that, cluster the samples based on the expression index, they can already see that the existing patients really clustered, patient tumors clustered by the subtype. So previously, the subtype was already determined by pathologists based on other histopathological features. And so without knowing anything about those subtypes, if the scientists just cluster all the tumor samples, you can already see that they cluster by the different subtypes. And so in this case, if you have a new sample and you do the same clustering and it cluster with this group, you will know, okay, that's a Lumina A subtype of breast cancer. But if it cluster with this group, you will know that it's a basal-like breast cancer. And that's kind of an easy way to do sample classification using this clustering approach. In this 2001 study, it's kind of an ideal case that when you cluster all the samples together, they really cluster by the subtypes. In this situation, we have 6 different subtypes, but sometimes you can even do it easy, just normal versus disease, and just 2 classes. But really, even in the 2 cluster cases, there is no guarantee after you profile, say, 100 normal and 100 disease, you do clustering, that all the disease samples will cluster together and all the normal samples will cluster together. And so in this situation, very often you need to examine the cluster result and see whether things cluster well. And then if things don't really cluster, supposedly after you do this, the samples don't really cluster by subtype. You might want to change the linkage, right? Maybe after changing the linkage from the average to the complete to the single linkage, the separation is slightly better, then you can use that as well for classifying your new sample. But you can see here, once you change the linkage, you are trying to see whether you can separate the two groups better before you put in the new sample. This is not completely unsupervised. It's kind of semi-supervised because you are trying to see, whether the class labels are already grouped in this clustering approach. Remember, for unsupervised is before you test your unknown sample, you don't even care about the known samples. You just want to cluster them. Then you put in the new sample. But very often, if the known samples don't cluster well, people do try to try different parameters, try different approaches to separate them better. It's just not machine learning. It's like human trying to tune this thing, right? So it's kind of semi-supervised. But that's kind of the simplest way you can use for sample classification. Another approach that people use is called k-nearest neighbor. This is actually the simplest and most used instance-based machine learning algorithm. So instance in this case would be every sample that we have, some tissues, whether it's normal or disease or any conditions. And so we are assuming that all the instances are some points in an n-dimensional space. In our case, the n dimension is all the genes in the genome that you observed. And you can define the neighbors in terms of distance. This is probably looking at log TPM distance, the correlation between the two samples on the genes. And the K is the number of neighbors you want to consider. And so originally, when KNN was introduced in bioinformatics, it was very early days in microarrays. Because in the early days, each microarray, actually the size is probably this big, 1 square centimeters big, a glass slide. And you put a few thousand genes there, and these are sometimes hand spotted and sometimes spotted by a student devised little robots. And they will spot some probes on this array to test the expression of a few thousand to maybe tens of thousands of genes. But when you profile a particular sample, you put all the RNA on here, you try to do a readout on each spot. Sometimes there are spots that information is missing. And so at the end, when you get the expression matrix of all the genes and all the samples, you might see some genes missing. The missing data is kind of it's not an overall missing. It's just occasionally you might miss a cell in this whole big matrix. And so KNN was used quite frequently by scientists to impute the missing value. So for example, if in this big matrix, so the Y are the cell conditions or samples, and the X are the genes. So supposedly, if gene X in cell Y is missing, this is a particular spot on the big data matrix. What we can do is to find the K nearest samples to this sample Y. So you look at, supposedly you have 100 samples and then 6,000 genes, and there's one spot that's missing. For this one sample, you want to ask, let's look at this matrix. What are the K, let's just say maybe K equals 3 samples that's closest to this one, the one cell that has a missing value. And you can use all the remaining genes, just ignore the gene that's missing, use all the remaining genes to calculate their correlation, to calculate their distance, to see whether they are really similar. And you find the 3 sample or 5 sample that's most similar to this guy. And then after you find the K nearest samples, you can calculate the average expression of the gene X in those K samples. So supposedly you got 3 samples that's really close to this sample that has missing value. Let's now look at the gene in those 3 samples and take their average, and you use it as a to fill in the missing value in this particular condition. it actually, most of the time, it works reasonably well. So occasionally when you have these kind of missing value, you can use KNN to fill it in. Yeah, so this is kind of the microarray case. You can see you want a matrix to be fairly full, but occasionally there might be a missing value. Then you can use the remaining samples and their expression level on this gene to help you impute. So you can also use k-nearest neighbor for classification. So for example, supposedly we have previously profiled some disease samples and some normal samples, and supposedly we can project them into some space. You can use correlation to calculate their distance. So for any observation, for example, an unknown sample that we don't know whether it's disease or normal, we can find the K samples in this whole big matrix, or the whole data set you have in the training data sets that's closest to my unknown sample. In terms of, for example, log TPM, these K samples might be the most correlated to my sample of interest. And then we just ask, okay, for those K nearest samples, are they disease or normal? And then based on the majority voting, we can assign whether this new sample is gonna be diseased or normal. And so you can see here, KNN depends on a few things. The first, that you need a proper distance measure. If you have too many irrelevant feature attributes, it wouldn't work. I think for a gene expression, you can just look at the TPM level. You might eliminate genes that are not expressed at all, that have small variations. That's okay. But you need a proper distance measure, and also make sure you don't have too many irrelevant noise in the data to skew your overall sample distance. But after that, for each sample, in order to make a prediction, you just look at the closest samples to this unknown one, and based on majority voting, decide whether this unknown sample belongs to a disease or a normal. And so you can see, depends on where your unknown sample is. The one I show here, it might be a tricky issue because it lies right on the boundary between the two. Whereas if you have a sample that's around here, maybe it will find the 3 nearest neighbor around all the blue dots. And if you have a sample around here, you will find the 3 red dots around it. That will be an easier prediction, right? And so question is, how do you determine how to choose K? You can see this is how they actually do it. K can be determined by the predictability of the known samples. So supposedly, we have some samples that are normal, and we have some samples that are diseased. And then there's an unknown sample in here. We're trying to predict whether this guy is disease or normal or disease. What we can do is, if we don't use this unknown sample, just look at the known samples. Well, we can try a K of 3 or 5 or 7 or 11 and see how well this K works to predict the known samples using the majority voting, and see which one give you the best result. So in here, K, usually people pick an odd number. This is just in case you have a tie, because if you have 2 samples saying this is normal and 2 samples saying this is disease, then at the end you just still cannot make up your mind. But if you have 3, 5, or 7, you will always have a majority voting to make a decision. But you can imagine, if you have to use the existing samples to decide whether the K should be a 3, 5, or 7 that give you the best prediction, it is again semi-supervised, right? Because you are looking at the existing samples to help you determine how to select this parameter in order to predict this new sample, whether it's disease or normal. So KNN, you can see it's a pretty simple idea. It's kind of a guilt by association. You know, this sample should look similar to be assigned to the same class where their expressions are similar. It works well on many practical problems, and it's fairly noise tolerant, and it's very easy to implement. Unfortunately, it offers very little insight. You just look at overall gene expression, you hopefully that they will cluster. If things don't work, well, too bad. It basically, whatever distance measure you give it, it will try to give you some k-nearest neighbors. But it's kind of a simple thing to try. If you have a lot of samples available, you could actually try it out. It should work pretty well. Another approach that people are using is called multidimensional scaling. So this, supposedly we have a gene expression that's usually 20,000 genes, right? You have a number on each of the genes. With RNA-seq, you usually probably only have value on 10,000 genes. The remaining 10,000 may not be expressed. There are thousands of genes that are not expressed in a condition, but still it's a very high dimension data set. Multiple dimensional scaling is trying to optimize or approximate the pairwise distance relationship as much as possible in lower dimensions. So supposedly we have a number of samples, A, B, C, D in this case. The A, B, C, D can be continuous, can be anything that you can come up with, as long as you can provide a distance measure. So in this case, it is also symmetric, which you only need to look at half of it. I think for RNA sequencing, you can use just half of it because the A and B correlation should be the same as B and A correlation. And so this is saying, this is the distance, A and B have a distance of 90. So the matrix is a dissimilarity matrix, is their distance. Whereas in this case, A and C are very similar, their distance is 10. B and C, their distance is 80. And so basically you calculate the pairwise distance between every pair of samples. And so in this case, if we only have one dimension, if we only allow the algorithm to draw in one dimension, it will try to approximate the pairwise distance, which will recapture the pairwise distance as much as possible. So you can see in this case, A and B are really far away because it's 90. A and C is the closest there, it's like 10. And the next one is B and D. You can see B and D are pretty close. C and D is 45. Yeah, so it roughly captured the distance. This is easy when you have only 2 samples, but imagine you have 100 samples and the distance is calculated with pairwise distance. When you try to draw this in a single dimension, you may or may not be able to capture all the distance. There will be some things that there are discrepancies, but this algorithm will try to approximate or try to optimize the pairwise distance relationship as much as possible. And so depending on how many dimensions you allow, basically, yeah, so there is no guarantee you can completely capture all the pairwise distance. If you have all the dimensions as your original gene expression, then yes, you can capture everything. But when you have lower dimensions, you may or may not be able to capture it. So if you have single dimension, there might be a lot of things that are not quite fitting with your data. It's just trying its best. But when you are allowed 2 dimensions, then there are some distance that it allows, it's fewer constraints. It allows more of this distance matrix to be better captured. It will better reflect the pairwise distance. And if you allow a 3rd dimension, you will even better reflect the pairwise distance. So the more dimension you allow, the better it can capture the original data, even though basically the algorithm will find in each dimension that best to capture the pairwise distance, okay? And so in this case, it's trying to capture things in 2 dimensions. Supposedly each dot in here is a sample, and the red dots belong to, say, the disease class, and the blue dot belong to the normal class. And then if you have a new sample coming in, it also, you calculate the pairwise distance of this sample with all the other distance. It's kind of like a k-nearest neighbor, right? But it's looking at all the samples together, not just the 3 nearest in some sense. And it's trying to use all its neighbors together to try to predict whether this new sample is gonna be belonging to the disease cluster or the normal cluster. So you can see here what the input of this MDS is a distance matrix. So you provide the distance matrix, then it will be able to give you a 2 or 3 or whatever dimension you allow it to project to. And there is no requirement for the conversion of the original data into a linear form. As long as you can calculate their distance, it can project into 1 or 2 or 3 dimensions as you need to. Okay, so that's another way we can separate out the samples and figure out whether the sample is a disease or normal, or yeah, any classes you want to look at. Questions about MDS? Yes?
How does projecting the data in all dimensions
work? So you can see in here, you can see basically this is not really a projection. You just try to draw it in 1 dimension, right? You just try to draw it, and the algorithm, I guess for this course, we will not be able to go through all the math on how they calculate this. It just try to approximate all the pairwise distance. No, you assume that the numbers in here are the correlations between every pairs of samples, right? So for example, in your, say RNA-seq, you get a TPM. Usually people calculate this distance at the log TPM level. Otherwise, the very high because remember the gene expression, there are some highly expressed genes and they have also very, very high noise. And so if you're just calculating the correlation based on the raw TPM, it might be skewed really towards those high genes. So you take a log to kind of scale it a little bit. And once you have the log TPM, you can calculate the pairwise correlation of every sample. And that will kind of give you a distance.
So that's the correlation to log all genes.
Of all the genes, yeah. Yeah, so sometimes when the expression level is 0, right, TPM is 0, you might give it a little pseudo count just so that you don't take a log on 0. Yeah, but so usually it's doable on this. Yeah, so basically, as long as you can provide this matrix of distance, it will be able to make the projection. The more samples you will have potentially more conflict if you try to project them into only 1 dimension. So maybe a 2nd dimension will help, the 3rd dimension will help even more. Okay, if you only have few samples, maybe a single dimension would be sufficient. Okay.